Hey everyone, welcome back to my Calculus 1 series. In today's lesson, we're going to be going over the area under a curve. Today's lesson is the official start of integral calculus, and it's going to be an introduction to the underlying concepts of what an integral is. This lesson is going to be very hefty, and I suggest you go back and review it, because if you don't understand this, then integration itself won't really make sense. So before, we were solving problems where we had, let's say we had some sort of graph look like this, and then we were interested in the rates of change at particular points. So here and here, right? Let's say there. Now what we're going to be doing is we're going to be solving the problem of what if we have a graph, something like this, same one, and what if we want to find the area under it, let's say all of this. How do we go about solving that, right? This isn't a regular shape anymore. We don't have like a square and then we can just use like area equals to side squared, or we have a rectangle and then we can use area equals to length times width. We don't have that anymore. We have this very curved graph, and we're trying to find the area under it. So in today's lesson, we're going to be going over how we can approach solving this problem by using formulas that are already well known. For example, we're going to be using this one a lot. So I'm going to go ahead and show you how we can approach this problem of trying to find the area under a curve. So again, here's the problem. Let's say we were given this curve y equals x squared, and sorry, it's a little lopsided, but again, it's because it's freehanded. But let's say that this is y equals x squared, and we are asked to find the area between the intervals 0 and 1, x equals 0 and x equals 1. Let's say this is going to be 0.11, and we are asked to find this area under here. So the way I propose we approach this problem is we first split it up, let's say, into 4 rectangles. So we're going to have a split here, and a split here. Okay, this right here is going to be 1/4, this right here is going to be a half, and then 3/4. I suggest we split the area up and we find the areas of each individual, let's call this a strip, right? And then we can just sum them up. And then that would give us the total area under the curve for that specific little interval. However, again, we are faced with the problem that the side right here of this little strip is curved, and we don't know how to find the area under that. So again, I'm going to say that let's use a well-known formula where area is equal to length times width, and this is the area of a rectangle. So let's make this little area into a rectangular shape. Now there are a number of ways I can go about making this little strip right here into a rectangle, and I'm going to show you some of the more common ways that we can do this. So here are the 3 most common ways that we can draw these strips of rectangles. So the first way is the left endpoint. Basically, again, we're going to split this area into quarters, which they're all split right there. And then we're going to take the left endpoint of each rectangle or each interval or strip, whatever you want to call it, and we're going to draw that upwards to the graph and draw a rectangle there. So the first point starts off here. Now we move on, because this interval is covered, we move on to the next interval right here. Now on this interval, we start off right here, and we're going to draw this upwards to the graph, and then we're going to draw this rectangle that you see, this red one, that's shaded in, and we're going to connect it. Then we do this for every interval. We go on to do this for this interval, and then lastly for this interval. And you can see now that we've kind of approximated the area under this graph. However, we are missing some sections, like right in here or right in here. Now we can go on to do the right endpoint method, and basically we're going to split it up into the same sections. As we can see here, there are 4 sections, and what we're going to do, instead of using the leftmost endpoint of that the rectangle, we're going to use the right endpoint. So in this case, we're going to plot this black dot right here, because that is the right upper edge of the right upper corner of the first rectangle, and we're going to draw that rectangle there. And then we do this for every interval. So as you can see here and here and here. However, I have not shaded these parts in with red, although we are going to include them in our calculation. I didn't include them because I figured that the graph would be a little more difficult to see, but we are going to include these parts right here too. And now, as you could see, before we were kind of underestimating because we were missing parts. Now we're overestimating because these rectangles are kind of sticking out to the side, and they're taking in more area into account than what actually is under the curve. The last most common method is probably the midpoint method. And instead of taking the right top corner of the rectangle or the left top corner of the rectangle, we're just going to take the midpoint of the rectangle. And as you can see, again, we have these four intervals right here. And in each interval, instead of taking the right or left top corners, we're just going to take the midpoint of that rectangle, and then we're going to draw kind of a rectangular box. Now, you could see here that the approximation is still like overestimating because of these little corners in here, but it's a lot better than the right endpoint method. So actually, now let's go ahead and calculate the areas for each of these three methods. So firstly, the area for this one. This one is going to equal to, basically we're just going to sum up the areas of each of these individual rectangles, right? So the area of the first and leftmost rectangle, the one right here, the one that the arrow is pointing at, this one is going to be 1/4 times the height of that rectangle, which is 0. Now the next rectangle, it's also going to have a width of 1/4. However, what is the height of this rectangle? Well, we know the x value over here, and the x value starting this interval is going to be 1/4. Because the length of each interval is 1/4, we know that the second rectangle, this one over here, the x value of its left upper corner is going to be 1/4. If we draw that point upwards to the graph, all we have to do to find what the y value of that point will be is to just apply the function to that x value. So we can say that it's f of x, where x is equal to 1/4. Now if we continue to do that for every point, let's do this for the next point. The next point will be right here. And the x value at this point right here on the graph, this black one, is going to be now 1/2 because we're going to have an x value of 1/2. So we're going to take the width of this rectangle and we're going to multiply it by the value of, so the height or the value of the function evaluated at that x value. So f of 1/2. And we're going to do this for the last point too. Except now this left upper corner has an x value of 3/4. So it's going to be f evaluated at 3/4. So now let's go on to simplify this function notation and actually figure out what these values are. So again, we're going to start off at 0² plus 1/4. F at 1/4, we know that the function is x squared, so this would be 1/4 squared. And we're going to do that for every function notation that we see here. So there we go, we have simplified the formula, and if we go on to calculate this, it will end up being 7/32, which is roughly 0.21875. So there we go, we have calculated the area under the curve using 4 rectangles and using the left endpoint of them. So obviously this is going to be a bit of an underestimate. Now let's go on to the right end. So again, the area of each rectangle is equal to the length times the width. The width of each rectangle right here is going to be 1/4. So for the first rectangle, the area is going to be 1/4 times f evaluated at this point right there. And what is the x value of that black dot? Well, we know because the interval's width, this little rectangle width, is 1/4. That means the second rectangle starts at 1/4, or we can kind of say that the first rectangle ends at 1/4. So this black dot right here, the first black dot, will have an x value of 1/4. Now we go on to do that for the second rectangle, and this one is going to be f evaluated at, this will now be 1/2 because we will have 2 intervals of 1/4. So this will be f at 1/2, and we're going to add on the area of the next triangle, the third triangle, or sorry, rectangle, this one, and this black dot right here has an x value of 3/4. So the height of this third rectangle is exactly the height of this dot, which is equivalent to the function evaluated at that x value. And lastly, we are going to add the area of the last rectangle, which has a height of f at 1. Now let's go on to simplify this. So there we go. We've gotten rid of the function notation because we know that f of x is equal to x squared. We can just sub in this expression in place of the function notation. And if we go on to compute this area, it will be roughly 15 over 32, which is roughly 0.46875. Now, as you can see, we've gotten a much larger area, almost double the area of what we got using the left endpoint method. But again, we know that this right here is going to be an overcomputation because we are accounting for these extra pieces of these rectangles. So now on to the last method, which is the midpoint method. And the calculation is going to go in a similar way. We have 4 rectangles. We want to sum up the area of all 4 rectangles, and we're going to say that that's the area under the curve. The area is, again, the area of a rectangle is equivalent to length times width. The width of each rectangle is going to be 1/4. And now the height of each rectangle is going to be at this black dot right here. But this black dot is the middle of the rectangle, right? So if the rectangle has an width of 1/4, the midpoint of this rectangle, right? Let's say this is all 1/4. The midpoint of this rectangle right here is going to be at 1/8. So the first one will be f at 1/8. And now we can go on to sum up the other areas. So this black dot will have an x value of 3/8. So the height of that rectangle will be f at 3/8. The third rectangle will have an x value of 5/8. And the last rectangle will have a value of 7/8. So now if we go on to simplify this and get rid of the function notation, it will look something like this. And again, we're getting rid of this function notation, and we're using this now because f of x is equal to x squared. So all we do is we take the x value, the input to f, and we plug it into here. And we put that expression instead of f of whatever it was. So now if we go on to evaluate this, we will get 21 over 64, which is roughly 0.328. And now you can see that the midpoint is kind of in between both the right endpoint and the left endpoint. Now it's important to know that we see that in the left endpoint we are underestimating, in the right endpoint we are overestimating in this case. So we know that the true area of this of the area under the graph will lie somewhere in between using the left endpoint and using the right endpoint. I'm going to use this little notation right here. So we know that the area is somewhere in between these two extremes. Now, one of the things that we can notice from this immediately is that we've only taken 4 strips or rectangles, whatever you want to call them. And we can notice that if we were to take more strips, there would be even less area that we're accounting for. For example, if we're using the right method, if there's less of these rectangles, there's going to be less of these strips hanging out. And likewise, if we were to take the left endpoint method, if we were to take more rectangles or strips, there would be less of this area missing. So I can go on to show you really quickly right here. I'll just show you a comparison of using the area between 4 rectangles and then let's say maybe 8 rectangles. So here's a quick comparison between us using the right endpoint method with 4 rectangles and 8 rectangles. As we can see with the 4 rectangles, we have these huge areas that are kind of, this is what's causing us to overestimate the area under the function. However, if we switch over to something like 8 rectangles, we could see now that the area that we're overestimating has become significantly less. We no longer have these huge chunks of area that are just sitting there. Because the intervals got so much smaller, the overestimate becomes much less. Now, if we were to use a lot more rectangles, we can see that quickly the area is going to become more and more accurate. So that is one thing to notice about this method of approaching like the area calculation under a curve. And we're going to see later on in the lesson as to why this is important. So now that we've done these calculations right here, the left endpoint, the right endpoint, and the midpoint method, right? What is the true area? Like, which of these numbers is closest? Obviously, it seems that this one is, because it's like we could see from the graph that the overcalculation is very little. So it seems to us that this one is the more accurate one, but truly, what is the area under this curve of f of x equals x squared between the interval of 0 to 1, right? So what is this area? Before we were approaching this problem with 4 rectangles, however, now we're going to approach it more like generally, and we're not going to say we're only going to have 4 rectangles. We're going to have n rectangles. Now let's assume that instead of 4 we have n rectangles. So how do we go about computing this area, right? The area of each subinterval or rectangle depends on 2 things, right? Because the formula for area is length times width, right? It depends on the length and the width. So first, let's go on about width. So the width for each rectangle really depends on how many rectangles we have. If we go back to this diagram, we could see that the width of each rectangle here is 1/4, because we have the total length of this interval, all of this is going to be 1. But we have 4 rectangles, so we divide this by 4 and we get that each rectangle has a width of 1/4. However, we could see that in the case of 8 rectangles, we now have the same total length. It's 1. But now we have 8 rectangles, so each rectangle now has a width of 1/8. So the quick way we can do this calculation is by saying that the change in x, or the width of them, right, it's equal to b minus a over n, where n is the number of rectangles. So here's our little formula for calculating the, I called it delta x, but it's basically the width of that rectangle, the arbitrary rectangle, whichever one we're talking about. So we can compute it by saying, okay, what is the length of the interval? We know that the length of the interval can be found by using the start of the interval and the end of the interval, right? If we have, let's say, we start at 2 and then our x ends at 4. Well, the length of this interval is 2. How did we compute that? We would take the end point, which is 4, and subtract the start point. So that's exactly what this top right here is doing. It's taking the end interval, which is b. Let's assume that we have an interval a to b. Actually, in this case, it's 0 to 1. B in this case is going to be 1, and the start is going to be 0. The top, the numerator of this delta x expression, is basically taking away the start endpoint from the end endpoint. We're trying to find the distance between the 2 endpoints, right? But then we also need to know what is the area per rectangle, right? And if we have this total area and then we have n rectangles, the area per rectangle, all we have to do is just divide that by n. Like I said here, if we have a total length of 1, right, and then we have 8 rectangles which are supposed to fit in here, well, what is the area, or sorry, the width per rectangle? Well, it is 1/8. Likewise in this example. So that's what we're doing here. We're taking the number of rectangles, and then we're trying to find the total length of the interval, which is this b minus a, and then we're simply dividing the total length of the interval by the number of rectangles that we would have on that interval. So that is how we can compute the width of a single rectangle. Again, let's remember, we are computing this for each rectangle, not all of the rectangles. We are computing this for each individual rectangle. That's why I wrote each rectangle. But now that we found the width, let's find the length of each rectangle. Well, again, the length of the rectangle, right? If we go back to the diagrams, we can quickly see that the length of the rectangle, this portion right here, depends on where we are on the graph. It depends on this point right here. In the case of the right endpoint method. In the case of the left endpoint method, it will depend on a different point. But in the case of the right endpoint, it depends on how high up we are on the function. And we could say that the length, or the height, I'm going to put in brackets here, height of the rectangle, depends on the function, right? But now we need to know, what do we input for the function? And it's important to know that there is like this distinction, because the function at this x value is different from the function at this x value, and it's different from the function at this x value. So we need to know what x value we put in. And again, let's start off by putting in xi, right? Where this is a subscript. Maybe I should make it a little smaller. So it's going to be x subscript I. And xi in this case is going to be the ith x that we're on, right? So if we go back to here, this right here is the 0th x, but this right here is the first x, this right here is the second x. So we need to know what x value we're on. And the way we can do that is simply by taking the amount of change, right, and then multiplying that by however many rectangles. So let's say we needed the third right here, the third x, right? The third x value. What we're going to do is we're going to take this, the width of each rectangle, and we're simply going to multiply it 4 times, because in this case we have 1 rectangle here, 2 rectangle here, 3, and then 4. So we're going to take 4 rectangles, and then we're going to multiply this by the width of them, which I said was delta x. However, that will simply give us the distance that we'd have to shift, right? We got lucky in this case that we're starting from 0, but if we weren't starting from 0, if we were starting from, let's say, 1, right, then we would need to add a value of 1 to that. So xi can be expressed as the start value plus delta xi, where I is the number of rectangles that we need to move over. So let's say we want to figure out the area of, the x value of the 4th rectangle, then I would be 4 in this case, and delta x would be the width of each rectangle, and a would be the start point. So there we go. Now that we have figured out what the width and the length are, or the height of each rectangle, we can go on and start breaking down this problem right here. So, okay, if we look back at here, what we've been doing this whole time is basically we've been finding out the area of each individual rectangle and then summing them up, basically adding up the areas of each individual rectangle. So let's approach this problem the same way, except now we're going to have n rectangles instead of 4. So I'm going to make the same computations. So firstly, we want to compute the width of each rectangle. Well, the width of each rectangle we know can be represented by this formula, but I'm not a big fan of memorizing formulas, so I'm going to simply go over how I make this calculation. Again, first we want to find the length of the interval. The length of this interval we said was 0 to 1. So the way we can compute the length of an interval is by taking the endpoint and subtracting the starting point. Okay? And this is going to equal to 1. So the total length of this interval is 1 x unit, or x value, whatever you want to call it. But now we want to find out the width per rectangle. And how many rectangles do we have? We have n rectangles, so I just need to make a simple division. So this right here is equal to the width of each rectangle. Now that we found the width, let's find the length or height. So the length or the height is going to equal to the value at that x value. So essentially it's going to equal to this, right? So it's going to equal to the function evaluated at the ith x. And we don't know what the ith x is yet, but I'm going to go ahead and find that right now. So I've drawn out a little diagram to help us find out what the ith x, or an expression for the ith x, will be. And we've assumed that we have n rectangles here, and that the width of each little interval is going to be 1 over n. So let's say I want to find the x value of the third rectangle, right? So the first rectangle is going to start off here. This is going to be the second one, and here is going to be the third one, right? And if we think about it, I've added 1 interval, 2 interval, 3 interval. So what I do is I take 3 times the width of the interval. I'm going to write it as delta x, but we know delta x is 1 over n. And then I'm going to add 0 to it because we started off at 0. What I was trying to say before is if this function had went something like this, let's say, and then we're asked to compute it from 1, let's say this is 1 to 2, right? We need to factor in the fact that we're starting from here, from the start point. So that's why I'm doing this addition, right? Let's say each interval, again, we have n intervals, let's say in this case, and then each interval has a width of 1 over n. Let's say I want the third interval, right? So I'm going to calculate how far over I went. It's going to be 3 times the width of each rectangle, but this isn't the actual width. It's not the x value that I'm looking for of the ith rectangle. The x value of this ith rectangle will be this plus 1 because we need to account for this shift. So that's what I was saying. For this example, we got kind of lucky that we started at 0, but we need to account for the start value. So the xi in this case will be 0 plus, and again, we want to go over n units, right? We don't know what that is, so it's just going to be delta x, which is the width of each individual rectangle, times I, which is the number of units that we want to go over. And if we look, it follows the formula right here. Again, I don't like memorizing these formulas, so I kind of derive it on the fly. But if you are a fan of memorizing stuff, then definitely just remember this one. You basically take your start interval, and then you want to add the amount of times you want to go over. So the amount of rectangles you kind of want to skip over. So now that we found xi, we can also find f of xi, right? So actually, let's simplify xi. So xi is just going to equal to delta x times I, but we know what delta x is. Delta x is the width, and it's 1 over n I. So this is going to equal to I over n. Now f at I over n is going to equal to I over n squared. So now that we found this right here is going to be the length or the height of any rectangle, and we've also found the width, which is going to be right here. So now let's take the sum of all the rectangles, right? We can express the area per rectangle to be equal to the width times the length, which is also going to be equal to 1 over n times I over n squared. And now we want to add up these n rectangles. So let's think about how we can do that. So the area for the entire thing, this capital A, is going to equal to the area of the first rectangle. So the first rectangle is going to have a width of 1 over n, and it's going to have this I right here tells us which rectangle we're on. So we're on the first rectangle, meaning we're going to have a 1 over n squared. Now let's move on to the area of the second rectangle. Well, it's going to have the same width of 1 over n, but now we're on the second rectangle, so I is 2, and that's the area right here for the second rectangle. Now let's add the area of the third rectangle. And we're going to keep on doing this until we get to the last and final term. Because we have n total rectangles, this right here is going to be the final term, where I is finally going to equal to n. Because we have n total rectangles. That was the assumption that we made. So I'm going to go ahead and simplify this formula a little bit. I can see a bunch of common factors, so I'm going to do a little bit of factoring, and we're going to simplify this formula a little bit more. We can see that we have 1 over n as a common factor, and we can also see that we have 1 over n squared as a common factor out of everything, because we have this power and a denominator of n. So I'm going to go ahead and factor out 1 over n cubed in total. So there you go. This is what the expression would look like after we have factored out the 1 over n cubed, which was the common term. Now, this right here is a pretty well-known formula. Maybe you don't know it, but if you don't, here's your time to learn it. It's basically the sum of squares up to n, and n can be any integer. So this expression right here is actually evaluated to n times n plus 1 times 2n plus 1 over 6. There is a proof to it. Obviously, you can research it, but I'm not here to prove that. This right here is the formula, though. It's pretty well known. So you might have come across it, you might not have. If you haven't, here it is. And now we're going to basically sub this formula in for this right here, because this is a lot more readable than this like dot 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 notation all the way to the end. So we're going to use this formula instead. I'm going to go ahead and simply plug that in. There you go. Now I could see common factors on the numerator and the denominator, one being here and here. So I'm going to go ahead and cancel these out. So there you go. Now we have a simplified expression of the area under the curve of this function with n rectangles. However, we haven't really specified what n is. What is n? Like, how many rectangles is enough? And if you remember, I said the more rectangles we have, obviously the more accurate the area will have, because we'll have less and less air. So as I was saying, as of now we have n rectangles, but we don't know what n is. N could be 10 rectangles, n could be 100 rectangles, n could be 1,000,000 rectangles. We don't know, so we need to assign a value to n. But we do want this value of n to be the greatest amount possible so that we can reduce the error as much as we can, like I said before. And one way that we know how to do this is by taking the limit of it. So we want to have the smallest amount of error possible, which means that we want to have the most amount of rectangles within this interval, right? So we want to have n as close as we can to infinity, right? Because we want to have the most amount of rectangles, and n is the amount of rectangles, like we said right here. We said that we are going to have n rectangles right here. So n is the number of rectangles, but we want them to be really, really large. We want to have a really a big amount of them. So how can we do that? Well, one of the ways we know how to do that is if we take the limit as n approaches infinity, right, of this entire function right here of a, then we're going to basically say that, okay, n is going to be really, really large. So let's go ahead and simplify this. All I've done here was I've taken this large a and I've plugged in the value that we've had for a into it. So now I'm going to go ahead and simplify this limit. We know how to do that. We've been doing that for a while. So I'm going to go ahead and fast forward through this. So there we go. We have computed this limit as n gets really, really large. And we can see that the total area that we would get is 1/3. And if we go back to our calculations, it's exactly like we predicted. Where were they here? Using the left endpoint method, we're going to get an underestimation because we are missing these little, this little stuff in here. We are missing these little areas. So we're going to get an underestimation, which is right here. And if we use the right endpoint method, we're going to get an overestimation because the area of each rectangle is too large, and as we can see right here. However, the midpoint method is a little more accurate because we do have a smaller overestimation. So we can see that by having this here. However, now we know that the area under the curve of the curve y equals x squared between the interval 0 to 1 is supposed to equal to 1/3. Now, I know that was a lot, and I'm going to kind of review what we've done so far and some of the key takeaways that we should get from this method. Obviously, this whole integral calculus is all about calculating the areas under a curve, and we're not going to be doing this entire process of figuring out the length and width and then, adding it all up together and writing out all of these limits and stuff. That would be too long of a process. So I'm going to go ahead right now, write the key takeaways, and then we're going to figure out a way how we can kind of reduce this. So here's a list of all the key takeaways from this entire method of figuring out the area. Each rectangle has an area of length times width, okay? So we need to find out, okay, what is the length and width of each rectangle? So the length of each rectangle, or the height of it, depends on the function evaluated at the ith x. If we go back to the diagram, this is what I mean. This ith x will have a different x value than this ith x, right? They will both have different y values here. So we need to figure out which rectangle we are talking about. That's why we use fx subscript I, because we don't know what the ith rectangle is that we're talking about, right? Then we say that xi depends on which is the ith rectangle. Like I said, we don't know which one it is, right? The first rectangle, the x of the first rectangle will be at the start point plus only 1 times the width of the rectangles. But the second x value of the second rectangle will be the start point plus 2 times the change or the width of the rectangles. and likewise for the third one. However, the general formula for x, the ith x, is the start point plus I times the width of the rectangles, basically skipping over I rectangles before it. If we want to go to the fifth rectangle, then we're going to multiply 5 times the width of each rectangle, and then we're going to add on this starting point of where we started. And like I said, A is the start point of that interval. So now that we know what L is, the length or the height, right? Now we need to figure out what is the width of each rectangle. And the width of each rectangle depends on the length of the interval and the number of rectangles in that interval. Like I said, let's say we have a length of this, right? This is our entire interval. If we want to fit 2 rectangles in here, well, we can split this in half, and each rectangle will have this, like that width. But now if we want to switch over and we want to say that, okay, we want not 2 rectangles, but we want now 4 rectangles, right? Well, now each rectangle has a significantly smaller width. So the width depends on the length of the interval, which is the b minus a, b being the endpoint and a being the start point of the interval, and then n being the number of rectangles that we want. So that is what the width is dependent on. Now that we have the length and width of each individual rectangle, we say that the area under the curve is the sum of all these rectangles, right? And we've talked about the 3 different ways of having these rectangles arranged, one being the right endpoint method, which is right here, one being the left endpoint method. And I excluded the midpoint method because it was just going to take like a while and stuff. But essentially the right endpoint method, we see that it starts at x1. Why? If we go back up to where we draw it, we could see that this is x1 right here, right? x0 is the start point of our interval. It should be here. But the right endpoint method starts at x1, whereas the left endpoint method starts at x0. It starts computing the first area based on this interval right here, or based on this x value right here. So we know that the right endpoint method will start at x1, like indicated right here, and it will go on from there up to xn. However, the left endpoint method will start at x0, so it'll always kind of be lagging one behind, and that's why we end at x n minus 1. Now that we've computed this area, right, how many rectangles are there, right? And as we know, the more rectangles, the less error we have, because there's less, we're either missing less area or we're accounting for like less overestimates. So we want to set n, the number of rectangles, to be as many as we can have. And the way we do that is by taking the limit of the area, right, which is rn being right endpoint, and ln being left endpoint method. So this is going to be the formula for computing the area under a curve using this right here as the right endpoint method, and this is the left endpoint method. Again, we're lagging one behind in the left endpoint method. So this brings me to sigma notation, and if you haven't seen sigma notation yet, it's basically this sign right here. It's like an E. So the sigma represents the sum of all items that we're going to give it, right? So if I were to write an expression like this of I, right, it's telling us to add, this is saying sum from I equals 1. So this is the start. This right here is the end, right? The end is all the way to n, and it's telling us to take the sum of I. So this will look like, okay, the first time we go through it, I is going to equal to 1. And then we're going to add because it's the summation, and we're going to iterate all the way up until the end, which is n. So it's going to go I equals 1, then we're going to add I equals 2, then we're going to add I equals 3, all the way to I equals n. So this is what the sigma notation does. It basically is a nice way to compress an addition of like elements from like a start to a finish. It's a nice way to compress them into a single symbol, whereas like as opposed to writing it like all these like dots and stuff like that, as we can see up here. So this is really messy up there, and we're going to use sigma notation now to kind of compress it a little more. So the area using sigma notation. So if we write out what the area of the right endpoint was, it was the limit as n approaches infinity, because we wanted to have infinite rectangles, and it was going to be the sum, right, of each rectangle. And this is the sum of each rectangle right here, right? This is going to be the sum, sorry, this is going to be the area of the second rectangle, and we want to do this all the way up to f of xn times delta x, which is the width of the nth rectangle. Now, like I said, this right here is a sum all the way from x1 to xn. So we can express that using sigma notation, and all we say is that a is equal to the limit as n approaches infinity. We're going to keep this portion of it here, and the new portion, this right here, the stuff that I've kind of highlighted, this is going to equal to the sigma. We want to go all the way up to n, starting from 1, so I equals 1, all the way to n. And what are we going to sum up? Well, we're going to sum up these terms, right? Well, what is each term consistent of? Each term is consistent of f at x, right? We're going to leave out this little subscript for now, delta x, right? And as we could see, the only thing changing is the subscripts, right? It goes from 1 to all the way to n. So here, instead of putting those terms, we just put I. And now we have a nice and compressed method of writing the right endpoint method for calculating the sum of these rectangles or the area under a curve. Now we can write the same thing for the area using the left point method, and I'm just going to go ahead and fast forward through it. So there we go. Now we have the formula for calculating the area under a curve using the right endpoint method, which is here, and the left endpoint method, which is here, both written in sigma notation. And we can see it's much more compact, much more readable, and it's easier on the eye. So let's take a look at an example and apply everything we've learned about figuring out the area under a graph. Here's the example. We say let A be the area of the region that lies under the graph y equals e to the negative x between x equals 0 and x equals 2. And the question asks us, using right endpoints, find an expression for A, meaning the area under the graph, as a limit, and it's saying don't evaluate that limit, which is fine. So again, how do we go about computing this stuff, right? 1, we need to find the area of each individual rectangle. 2, we want to sum up the area of each rectangle. And lastly, 3, we want to have infinite amount of rectangles. So these are the 3 steps that we're going to take to finding the area under this curve right here, the y equals x1. And let's go ahead and start off with number 1. Number 1 is to find the area of the rectangle. We know that the area of the rectangle is length times width, okay? So let's go on to compute the length, right? The length we know is the height of the function at the ith x. What is the ith x? Well, the ith x is equal to the start value, which in this case, the interval is from 0 to 2. So it's going to be 0 plus, we can omit that 0 if we know it's there, but I'm just going to write it for now, plus the width of each rectangle times I, which is the number of rectangles that we want to skip. And now we need to find out what delta x is, right? But the width in this case is going to equal to delta x, and delta x is equal to the width of each rectangle, which is the total length of the interval divided by n rectangles. Okay, so again, b minus a, we know what the endpoint of the interval is. It's 2, and the start point is 0, and we're going to have for now n rectangles, but we eventually want to have that equal to infinity. So this is going to equal to 2 over n. So now that we've computed delta x being 2n, we can go on to simplify this even further. So we can say that x at I is going to equal to delta x times I, because we don't need that 0 anymore, and this is equal to 2 over n times I. So now that we have found xi, we want to find what f at xi is equal to. Well, f at xi is basically taking xi and plugging it in to the input. So it's going to be the same as saying this, right? We want to take the input and just plug it in for wherever x is. And the function is y equals e to the negative x. So all we're going to do is we're going to say that this is equal to e to the power of negative 2I over n. Now, this right here is the length. So we've computed the length. It's this. And the width for each rectangle is this. So the total area per rectangle is going to equal to e to the power of negative 2I over n times 2 over n. This right here is the area per rectangle. So we've completed step number 1, and now we want to move on to step number 2. We want to sum up the area of all rectangles. And we've learned how to write the sum. The sum is the sigma. We want to sum up all rectangles starting from 1 to n. N, we don't know how many are yet. And we want to sum up the area of all of them. What is the area of each rectangle? Well, it's given by this formula. So we can simply write e to the minus 2 to the power of I, or 2 times I over n. And we want to multiply this by 2 over n. Again, this right here is the expression for the area of each individual rectangle, and this sigma right here tells us that we're going to sum up all of these individual areas. So this is the area now. However, we haven't yet assigned a value to n, and step number 3 tells us to set n equal to infinity. And how do we do that? Well, we know we can do that through a limit. So we're going to take the limit as n approaches infinity, and we're going to keep this expression the same. So there you go. We have found an expression for the area under that curve between that interval using limits. So anyways, that was a very long lesson. I suggest you go back and ensure that you understand everything that's going on, the kind of the two main methods, the right endpoint method and the left endpoint method, the whole summation thing and how we find the area under a graph. Obviously, as we get further into integration, we'll see that things do become a little bit easier because I'm going to tell you, but the integral basically does that for you. This is just kind of like how things work in the background. Anyways, I hope you enjoyed the video. If it's helped you out at all, please like and comment as to what it's helped you out with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.